So Lewis structures are a way to draw out compounds showing what's happening with their valence electrons, their outermost electrons. I've seen them called Lewis structures or electron dot structures if you want to be more descriptive about what you're doing here. And what you are doing is showing the valence electrons. Let's start by drawing the Lewis structure of just an element. So nitrogen has 5 valence electrons. We know that from its position on the periodic table. And we had a little review of that at the very beginning of chapter 6 in the note packet. So we are going to want to show 5 dots around the nitrogen. So we want to spread out the first 4 before we go and double up. It doesn't really matter if you draw the 2 on this side or if you draw the 2 on top, just as long as one side has 2 and the other 3 sides have 1 each for a total of 5. So for carbon, there are 4 valence. So 1, 2, 3, 4. And for sulfur, there are 6 valence. So we need 2 sides that have 1 each and 2 sides that have 2 each for a total of 6. If you have an ion instead of a neutrally charged element, it would have a different number of electrons. So lithium as a neutral atom has 1 valence electron. So you would just draw lithium with a dot next to it. Lithium plus, you would draw this one as missing. So lithium plus has lost its valence electron, and so that could be drawn as lithium with a +1 charge, either with brackets or just lithium with the +1 next to it. The reason for the brackets is just to sort of help keep the electrons inside and the charge outside. It makes more sense with a negative ion like oxygen. Oxygen with no charge has 6 valence electrons. Oxygen with a -2 charge would have 2 additional electrons, so it would have 8 valence. And just to let you know that the oxygen has a -2 charge, we put brackets and put the charge next to it. So if you just have regular oxygen with no charge, you don't need to put brackets around it. You can just put the valence electrons. To show that the charge, normally it's shown with brackets to kind of keep it organized. So bromine with a negative charge would also have 8 valence electrons, bromide ion that is. So bromide ion would look like this with the 8 valence electrons. Bromine without a charge would have 7 valence. So here is bromine with 7 valence and with no charge, and here is the bromide ion. So let's try to show the Lewis structure of an ionic compound. We'll just draw the Lewis structures of each ion and put them next to each other. Lithium we've already looked at up here. Lithium with a +1 charge would have the 1 valence electron missing, so there'd kind of be no valence electrons in the outermost shell. Fluoride ion, fluorine with a -1 charge, would have 8 valence electrons, the 7 that normal neutral fluorine has, plus 1 additional electron. So that would have a full octet, and we would just kind of draw these next to each other. Calcium with no charge has 2 valence electrons. It's in that second group of the periodic table, the alkaline earth metals. And so it has 2 valence electrons when it is uncharged. When it forms a +2 ion, it has these 2 missing. So we could just draw it with no dots next to it. And then the oxide, we've already seen up above. Oxide ion with a -2 charge has a full set of 8 valence electrons. Magnesium with a +2 charge would be drawn in a similar way to calcium. And then each bromide ion would have a full set of 8 valence electrons. So this is how we would draw the Lewis structure of an ionic compound, just the Lewis structure of the ion and then just putting them next to each other. That's to show that they're not sharing any electrons. It's more common to see the Lewis structures of covalent compounds. If you want to look at this, valence means it's on the outside of an atom. Covalent means it's on the outside of 2 atoms that are sharing the electron. So we can show shared electrons in the Lewis structures of covalent compounds. First, let's draw the Lewis structures of the atoms separately, at least one representative, chlorine and the carbon. Chlorine has 7 valence electrons and carbon has 4 valence electrons. So this is what that would look like. And when you draw these next to each other, it becomes kind of clear that carbon wants to share electrons with 4 of these chlorines, and the chlorine only really has a spot to share with 1. Let's draw these in 2 different colors so you can see the 7 valence of the chlorine coming together with the 1 valence of the carbon. So chlorine brought 7, or carbon actually has 4. So here I've brought together 1 carbon and 4 chlorine. I drew the chlorine in a different color so you can see those 7 valence electrons around each chlorine and then the 4 valence electrons that were originally around carbon. When carbon and chlorine are sharing this pair of electrons, they can both have both. And so even though carbon started out with just 4, by sharing with 4 of the chlorines, now carbon has access to 8. You can see around the carbon 2, 4, 6, 8, a full octet of electrons. And each of the chlorines also has a full octet of electrons. So they've been able to fill up their outermost shell by sharing rather than by forming ions. Now, this gets kind of crowded with dots pretty quickly. So another way to show that shared pair is by drawing a line or a covalent bond. So when you're counting the electrons that are around each of these atoms, remember to count that line as a pair of electrons. So if you want to see how many electrons the chlorine has, 2, 4, 6, 8. Okay, it's happy it has 8. If you want to look at carbon, 2, 4, 6, 8. Okay, the carbon is happy with 8. Let's try this next compound. Nitrogen has 5 valence and hydrogen has 1 valence. Remember that hydrogen is too small to get 8 around it. Hydrogen is going to be happy just with 2. Let's do the same thing where I color code these. So here's the hydrogen, they have 1 each, the nitrogen has 5. Now at the end here, the nitrogen has 8. By forming 3 bonds, it was able to share enough electrons to get 8. And then the hydrogen is also full with 2 because hydrogen is just filling the first shell and the first shell can only fit 2. So even though hydrogen doesn't have 8, this is fine for hydrogen. Here it looks a little bit cleaner when you draw it with lines. And then when you check for hydrogens, just make sure they have 2. This bond counts as 2. When you check the nitrogen, make sure it has 8. 2, 4, 6, 8. All right, let's try this one with oxygen having 6 valence and hydrogen having 1 valence. Now when we check the oxygen, it has 8. And if we check either of the hydrogens, it has 2. So those are all set. And we can draw it with lines to make it look a little bit cleaner. So because atoms all want 8 valence electrons around them, we can notice some trends. We saw all of these on the previous page. Since carbon started with 4 valence electrons and wanted 8, it will form a compound that has 4 bonds and no lone pairs. Nitrogen starting with 5 will form a compound with 3 bonds and 1 lone pair. And oxygen starting with 6 will form a compound with 2 bonds and 2 lone pairs. And then our halogen, it already has 7, like we had chlorine on the previous page with 7, and so it only needed 1 bond. And then the other 6 electrons around it are assembled as lone pairs. So lone pair meaning that it just belongs to 1 lone atom. Let's illustrate this with a compound we just finished drawing, the carbon tetrachloride. The carbon is forming 4 bonds and has 0 lone pairs on it. The halogen, chlorine, is forming 1 bond and has 3 lone pairs on it. So the bond that's being formed is a covalent bond. That's a shared pair of electrons. That represents 2 electrons. That line represents 2 electrons. Each of these pairs of dots, we call it a lone pair. I mean, it is a pair, so each electron is not alone. It's part of a pair, but it's not being shared. So that's what we mean by lone pair. This pair of electrons is only sitting on the chlorine. It is not being shared with the carbon or with any other atom. So the chlorine is the lone owner of this pair of electrons. It's not shared, but it still is a pair. It's 2 electrons. So when we count the electrons that are in the valence shell of chlorine here, we get 2, 4, 6, 8. This line counts as a pair, so it's 2 more makes 8. Sometimes 2 atoms can share more than one pair. So we can have a double bond or a triple bond. These lines are just single bonds. They're just a single pair of electrons being shared. But we can share 2 pairs. A double bond would share 4 electrons, or a triple bond would share 6 electrons. Let's go ahead and take a look at what that would mean. Okay, so I've drawn 2 oxygen atoms here, each with 6 valence electrons. And we'll go ahead and bring these together and have them share 1 pair. So this is what that would look like, forming a single bond in between them. Sharing this 1 pair of electrons would not really get oxygen completely full. Each of these oxygen atoms only has access to 7 electrons. So in order to get 8, they would want to share a little bit more. So if these unpaired electrons also moved in between the oxygen atoms and got shared, then this would work out a little bit better, because now if there's 4 electrons being shared between the 2 oxygen atoms, this oxygen atom has access to 8 electrons instead of only 7, and so does this oxygen atom. And we can draw those 2 pairs as a double bond in between those 2 oxygens, which really is a bit easier to see. I think when you get double and triple bonds, the dots make it a little harder to figure out what's going on here. So this might be a little bit easier to understand. And remember, each of these lines counts as a shared pair or 2 electrons. So when you're counting this oxygen, 2, 4, 6, 8, you can see that it has all 8. And also, it is following this trend. Oxygen tends to have 2 bonds and 2 lone pairs in order to get 8 because it's starting with 6. That is true for this compound as well. Okay, I moved the oxygen over so that we could take a look at nitrogen. I tried just starting by forming a single bond in between these nitrogens, each nitrogen with 5 valence electrons. But unfortunately, we can see that each of these nitrogens is not completely full with an octet. 2, 4, 5, 6. There's only 6 electrons around this nitrogen. And so it's going to want to share some more electrons. It's going to want to put these guys in the middle as well. Okay, so now I have them sharing 6 electrons, and that is definitely better because now we can see this nitrogen has access to 2, 4, 6, 8 electrons, and this nitrogen has access to 2, 4, 6, 8 electrons, and you can still see that I haven't added or taken away any dots. There's still 5 kind of rust-colored dots from this nitrogen and 5 from this nitrogen. So the right number of electrons are there, and yet with a lot of sharing, they're each able to get enough. Again, this looks better with lines. I think it's just cleaner than drawing all those dots, but it means the same thing. 2, 4, 6 electrons being shared. Each nitrogen has 2, 4, 6, 8 electrons. And then you can also see that nitrogen is doing what it normally does, forming 3 bonds and having 1 lone pair. So here we have C2H4. I've drawn each of the carbons in a different color. So you can see this carbon has 4 electrons in brown. This one has 4 in blue. Each of these hydrogens I've drawn in green with 1 valence electron each. One easier way to maybe keep track of the dots is to just count at the beginning how many dots are you going to have so that you can make sure you don't lose any. And there should be 4 plus 4 each for the carbon, and then 1 plus 1 plus 1 plus 1 each for the hydrogens, and so we should have 12 altogether. 2, 4, 6, 8, 10, 11, 12. So right now we have 12. We'll just keep an eye on that. And each of our hydrogens we can see is happy with 2 electrons. That's all it needs. 1 bond and 0 lone pairs will bring it up to 2 electrons, which is all it wants. But these carbons want to have 8, and right now they each only have 7. So the way I've drawn it, it's probably pretty obvious that we want to share a little bit more. All right, so here we have some more sharing going on. We have 4 electrons being shared between the carbons, and that is better because now the carbon has 8 around it, and so does the other carbon. And each of the hydrogens have 2, so now everybody is happy. We'll just draw it with lines so that it's easier to see. So here is the compound with lines. We can count all the electrons, 2, 4, 6, 8, 10, 12. We still have 12, that's what we're supposed to have. The carbons each have 8, 2, 4, 6, 8. The hydrogens each have 2. And we notice that carbon is forming 4 bonds and having 0 lone pairs, which is what carbon is usually happy doing. So this is the right Lewis structure for C2H4. Lewis structures that I just made for those simpler compounds shows one approach of how to do it, just to draw the Lewis structure of each atom and then start putting them together, do a trial and error. But if you get some larger structures, then instead of trial and error, you can try this other more organized process. This first step is good to do even if you are doing trial and error. You have to make sure that the total number of valence electrons that you are supposed to be putting into the structure ends up in the structure. So this is a good way to double check, even if it's a fairly simple structure that you just put together using trial and error. Once you have the total number of valence electrons, some of the ones that we are going to do are ions, so you have to make sure you account for those electrons as well. Then you attach the elements together using single bonds. Try to attach them together in a way that's symmetric. So the least electronegative element is usually the first one that's in the formula as well. These single bonds take up some electrons, but once you've connected it, you might have some other electrons that you haven't used yet. And so then you're going to put those on the terminal atoms, the atoms that are on the edge rather than the central one. You'll put those first. If you have any left over, those will go on the central atom. And then at the end, take a look at your structure, and the central atom was the last one to get electrons, so it might not have an octet. You might have run out of electrons before you were able to make a full octet around the central atom, and so you can share with that central atom by forming some double bonds using the electrons that the terminal atoms have. Let's go ahead and try this with carbon dioxide as an example. So step 1, we're going to count how many valence electrons we want from carbon dioxide. We have carbon, oxygen, and oxygen in the compound. Carbon has 4 valence, oxygen has 6, and the other oxygen has 6. So the total is 16. So we have 16 valence electrons that we are going to put into our Lewis structure. This is not an ion, there's no charge here, so we don't have any extra electrons in the structure, just 16. So now we are going to attach them with single bonds, and we are going to put the carbon in the middle. Carbon is the least electronegative element, and also this makes for a more symmetric structure, and we're going to just attach it with single bonds. So this uses 4 electrons, 2, 4. So the remaining electrons would give us 12, and we're going to put that on the terminal atoms, 12. So we have 12 remaining electrons. We put them on the oxygens to give them octets, and that used up all 12. Then we would put any remaining electrons on the central atom. There are none remaining, so we can't do step 4. We have all 16 showing, 2, 4, 6, 8, 10, 12, 14, 16. There's no extra ones there to put on carbon. Okay, so now the carbon in the middle does not have an octet. There's only 4 electrons that are going around this central carbon atom. So it needs some more. It needs 4 more actually, so let's go ahead and take these 2 from this oxygen and share it. And then we'll also take these 2 from this oxygen and share those. And then the final structure would end up looking like this. So just to show you what happened here, this lone pair that was on the oxygen, instead of just letting oxygen have it, we had it become shared between the carbon and the oxygen. So that lone pair turned into this pair over here, the pair in this bond that I've highlighted in yellow. So we have shared those electrons without changing the number of electrons that are in this structure. If you count them again, you'll see we still have 16. 2, 4, 6, 8, 10, 12, 14, 16. So we have the same number of electrons, but now the carbon has access to a full octet of electrons, 2, 4, 6, 8. And remember, carbon likes to have 4 bonds and no lone pairs. So this is what carbon likes. And then each of these oxygens has 2, 4, 6, 8 electrons with 2 bonds and 2 lone pairs, which is what oxygen usually likes. So this structure is the correct structure. I'll redraw it, but it has all of the 16 valence electrons showing and all of the atoms happy with a full octet of electrons. So we'll show it over here where we have more room. Okay, let's try a couple more Lewis structures. Some of these are ions, so we'll have to take that into account when we count the total number of valence electrons. Let's go ahead and do that first. Count the total number of valence electrons that should be in each of these structures. And go ahead and pause it, try to come up with a total number before you watch more of the video. All right, for this first one, we have 1 nitrogen, which brings 5 valence electrons to the structure, and then we have 4 hydrogens, which each bring 1 valence electron to the structure. That would add up to 9 electrons, but overall this structure has a +1 charge. It's an ion. That means it's short 1 electron. And so we're going to take those 9 electrons and subtract 1, take away 1 electron to make it a +1 cation, and then the total number of valence electrons in this structure should be 8. For this second structure, this nitrite anion, we have a nitrogen with 5 valence electrons, an oxygen with 6 valence, and another oxygen with 6 valence electrons. That makes a total of 17 electrons, but there is a negative charge, so this structure has 1 extra electron to give it a negative charge. So we have to add 1 electron to account for the fact that it is a -1 charge anion. So our total in this structure should be 18 valence electrons. Okay, for this last structure, we have a carbon with 4 valence electrons, a hydrogen with 1 valence electron, another hydrogen with 1, and an oxygen with 6. And so that brings us to a total of 12 valence electrons. This one is not charged, so we don't have to adjust that. We can just use 12 as the total number of valence electrons. All right, that's the first step to figure out the total number of valence electrons in the structure. Now we'll go ahead and make a skeletal structure using single bonds. In this case, hydrogen is less electronegative than nitrogen, but we can't put hydrogen in the middle because hydrogen can only form 1 bond. So it is pretty obvious that the nitrogen has to be in the middle of this structure to make a symmetric structure. Then we've used 2, 4, 6, 8 electrons, and there's no more electrons that have to be put around the structure, but it looks fine the way it is because each of the hydrogens has access to 2 electrons and the nitrogen has access to 8. The only thing we can add is the charge, a little bracket outside the structure showing that overall this structure is 1 electron short, so it is positively charged. This one over here, we'll go ahead and put nitrogen in the middle. That does both make a symmetric structure and put the less electronegative element in the middle here. We have connected it with single bonds to make this skeletal structure. This only used 4 electrons, so we still have 14 left. We'll start putting those around the outside terminal atoms here. 2, 4, 6, 8, 10, 12. Any extra we can put on the central atom, so those last 2 we put on the nitrogen. This brings us up to 18. 2, 4, 6, 8, 10, 12, 14, 16, 18. So all 18 are being used. The only thing is that the central atom does not have an octet. It still needs a little bit more. It needs 2 more, actually. So let's just go ahead and share 1 of these lone pairs. We can just pick 1 of the oxygens and make a double bond to nitrogen. So now we still have our 18 electrons showing, and each of the atoms has a full octet. So the only thing left to do is to show that it's a negatively charged structure. All right, this one I'll go ahead and put the carbon in the middle, and then we have used 6 out of the 12 electrons. I'm not going to put electrons around the hydrogens because remember, hydrogens are small. They don't have a bunch of lone pairs around them. So I will just put them around the oxygen. That takes care of the other 6 electrons. We have all 12 showing. The only thing is that our carbon needs 2 more electrons to make an octet. So we'll share that lone pair from oxygen, and we'll have the carbon with a double bond to oxygen. And you'll notice that oxygen is now happy. It usually likes to have 2 bonds and 2 lone pairs. Carbon usually likes to have 4 bonds. So that is how those 2 atoms like to complete their octets. All right, there are some exceptions to the octet rule. The free radicals, we are not going to see any structures here in this course, but every once in a while a molecule will have an odd number of electrons. So we're going to have some unpaired electrons in the structure. And then this one is something that we do sometimes see in this course. I think we have this in our shape section just because this particular molecule is a very good example of the trigonal planar shape. We'll talk about molecular shape in the next section. So a lot of times textbooks like to list this structure to show the shape of it. And the boron here does not have a complete octet. So this is an exception. We're not going to deal with this for Lewis structures. We might just look at this molecule as an example of a certain shape, but we won't be asking you to draw a Lewis structure that does not have a full octet. These tend to be very reactive structures because atoms really do want to have that octet, and if they don't have the octet, they're not very happy, and so they're going to start reacting with other things and try to get some of those electrons. This is something that we see a lot more in 101. It's a lot more common, and these can be stable. So we don't look at this too much in this course either, but we do look at it a lot in Chem 101 because larger elements do not have too much of a problem being able to fit more than 8 electrons. And they form some other very interesting shapes when they do that, and we will look at those shapes in Chem 101. In this course, we'll just look at the beginning shapes here. One last thing I wanted to talk about regarding Lewis structures is the concept of resonance. So molecules existed before Lewis came up with his way of showing the structures and showing the electrons. And so some molecules are not completely accurately represented by a single Lewis structure. And so it's really kind of an average of 2 or 3 Lewis structures that you can draw. And one story that I read about this was about a Middle Ages traveler who saw a rhinoceros for the first time. And he came back and described the rhinoceros to his friends as a cross between a dragon and a unicorn, or something between a dragon and a unicorn, because the rhinoceros had very thick skin, powerful legs like a dragon, and yet it had a horn like a unicorn. And this is an interesting way to describe resonance structures because, like the dragon and the unicorn, neither one of the Lewis structures that you draw is going to be real. The real thing is somewhat in between the 2 Lewis structures that you can draw. It's sort of like an average of the 2 structures that you can draw. Let's go ahead and look at some example molecules. So first we have to draw a Lewis structure for O3, which is ozone. And remember, we start by figuring out the total number of valence electrons, and that would be 18 for this uncharged 3-oxygen molecule. And then we'll go ahead and connect the oxygens in a skeletal structure using single bonds. That uses 4 electrons. We need to use 14 more. Drawing lone pairs around the outer oxygens uses up 12 of those 14, and then we have 2 more left over to go onto the center atom. So here we have 18 electrons. Our center oxygen atom is short. It only has 6 electrons around it, not 8. And so it needs to share with one of these outer oxygens. But there's no reason to pick the left-hand side over the right-hand side oxygen or vice versa. You could imagine the left-hand side oxygen sharing its electrons to give this left-hand side structure, or you could imagine the right-hand side oxygen sharing its electrons to give this second structure here on the right. When you look at the structure of an ozone molecule, the bonds between the oxygen on the left and the oxygen on the right are actually even. And so the real structure is almost like, instead of 2 bonds on one side and 1 bond on the other, it's almost like there's 1.5 bonds on each side. So these 3 bonds are more evenly distributed than either one of these structures indicates. However, if we try to indicate the evenness of the structure and the 1.5 bond of the structure, then we can't really draw a Lewis structure that obeys all the rules of a Lewis structure. So this is not a proper way to draw a Lewis structure. These are both proper Lewis structures, but these proper Lewis structures are sort of imaginary representations of the real structure that can't be represented with a Lewis dot structure, unfortunately. So since we can't draw it like this, we have to draw these 2 Lewis structures and then just show that they both contribute to the real structure by putting a 2-headed arrow in between. So the real structure is in between these 2 possible Lewis structures that you can draw. So this is really the best way we can represent the ozone molecule using Lewis dot structures, is to draw both of the possibilities and then put an arrow in between. Here we have the nitrate ion, and the total number of valence electrons is 24. Let's make a symmetrical structure with nitrogen in the middle that uses 6 electrons. We'll start filling in the rest outside, and that uses up all 24 electrons. There's no more for nitrogen in the middle. However, nitrogen is still short 2 electrons. It only has 6, and so it needs to share with one of these oxygens. So there's not really a preference for which oxygen to share with. So we have a very similar situation to this ozone molecule over here, where we could draw a structure where it's sharing with this oxygen, we could draw one where it's sharing with this oxygen, we could draw one where it's sharing with this oxygen, and in reality, it's sharing with all 3 of these oxygens equally, which we cannot draw as a Lewis structure, but we can draw the 3 possible Lewis structures with an arrow in between. So here I have drawn all the possible Lewis structures, the one that shows the nitrogen sharing with this oxygen to the upper left, one that shows it sharing a double bond with the oxygen to the upper right, and one that shows a double bond to the lower oxygen. In reality, the nitrogen is evenly connected to all 3 of these oxygens, so it's like each of these oxygens is connected with 1 1/3 bonds rather than 1, 1, and 2, but that would not make a valid Lewis structure, so we're just going to express this ion. I drew the charge because it is an ion. We're going to express this ion as an average of these 3 possible valid Lewis structures that can be drawn for the nitrate ion.